take a week. I haven't looked at them yet, but usually weekends are when I have most of my free time. So I'll try and get to those this weekend. Thankfully, we're a smaller class, so that's probably doable. My 105, I have like twice as many people, and that's going to be more of a pain, but I'll probably do yours first then, so you win. Okay, let's now go ahead and start talking about our next chapter, which is going to be on aromatic substitutions. So we're finally now going to be able to take that pesky benzene or any of those other aromatics that we didn't recognize on the exam. Actually, there was only one, right? We're going to be able to substitute things onto it. So this is different to what we have done in the past with alkenes and alkynes. What we did last time were addition reactions. So if we were to add HBr to an alkene, we would end up brominating one of the positions, and we would put a hydrogen on another position, and we would end up getting rid of our double bond, right? Those were addition reactions. Here, we're going to be doing substitution reactions instead. So we're going to be replacing, which always use benzene, at least for the starting part, where we may start with other things later. But we're going to see that, I'm sorry, this should be an H. We're essentially going to be doing a whole bunch of reactions, tons of them, that will be doing this essentially. We're going to be taking benzene and replacing one of its hydrogens with something. And we're going to see that we have a whole lot of somethings that we have as options with this. And so we're going to finally actually start working with this. So let's take a moment to see why additions don't happen with benzene. If we go back to a comparison, we know that if we take an alkene and give it bromine, we get an addition product, right? We can add the bromine to our molecule. We're not substituting anything, we're adding it. And we saw that if we try and do the same thing with benzene, we do not get any reaction, right? We saw that because it's aromatic, it's extra stable. That means it has lower energy. It doesn't have enough energy to do an addition, because that's going to raise it in energy way too much. We're going to see that an addition here, an addition reaction to benzene, is going to be highly endergonic. So we're going to end up increasing its free energy. We can think of this essentially as endothermic as well. So we're going to be raising its energy. And so it's generally not going to happen as it is written right here. However, we're going to see that we can actually, instead of adding to it, what we can do is substitute onto it. We're going to see that we're going to, our first reaction, if I can get a hexagon, well, okay. We're going to see that our first reaction that we're going to learn about, we just need to add a metal to it that's going to act as a Lewis acid. That's going to actually end up making it such that we'll be able to react our benzene. But notice we don't remove our double bonds. Our double bonds are still there. We're still going to have an aromatic compound at the end of our reaction. And so we're going to see here that we need some help to get this to happen. And in this case, we're using a Lewis acid. In this case, the iron is going to really form iron 3 bromide. And we're going to take a look at how this is going to help our bromine to react. So remember, when we first talked about alkenes, I guess we didn't, but whenever you first learned about alkenes, you saw that alkenes were both electrophilic and nucleophilic, depending on the situation, right? Depending on what they're put with. And we're going to see that the first kind of, or most of the reactions that we're going to be focusing on are going to be electrophilic aromatic substitutions, where our benzene is going to be the nucleophile. So we're going to look at a whole bunch of different electrophiles that are going to be strong enough electrophiles that benzene will react with. And so what happens here is we're going to end up actually putting a fourth bromine onto our poor iron here. Or what's more accurate to say is that we're going to end up, and no, we can keep it there. We're going to see that we're going to end up, a negative charge on our iron. And we're going to see that this bromine is going to have such a strong positive, almost a full positive. We could even consider it a full positive. I'll put that in light blue. We could consider this bromine to be positive. And as a result, we're going to see that we can have our benzene attack it, because it's going to be such a better electrophile than just bromine by itself. Remember that bromine by itself is completely nonpolar, right? Just plain old bromine. But if you remember way back to chapter 8, maybe, when we did alkene reactions, we saw that because of all the electrons in bromine, you can get a transient dipole, much like we do with London dispersion forces, way back when we covered those in 101, I guess, where, you know, the electrons just kind of happen to shift to one side of that molecule, and you end up with a partial positive on one bromine, partial negative on the other, and then it can react. That's kind of, you just have the transient dipole only here. But here we have kind of a full dipole, or almost a formal charge. And so as a result, because this is more positive, this means that it is going to be much more electrophilic. Right? We want our electrophiles to be as positive as possible. Nucleophiles, we want them to be negative, right? For them to be strong nucleophiles. And so as a result, we can end up kind of with this idea. So let's go ahead and see what's going to happen here. So if we're going to have a strong enough electrophile, we can go ahead and use our benzene as nucleophilic. So let's go ahead and see what's going to happen here. Another way we often describe this catalyst, our Lewis acid, is we can do it in 2 steps instead. But I tend to be lazy, but I should be good, shouldn't I? Fine. Okay. As we know, iron 3 bromide, standard compound, right? We can also use aluminum, by the way. Works the same way. If you throw Br2 onto it, what technically happens is you have both bromines going on. Let me redraw it, actually. Don't worry, you do not need to know this formation process, for those of you who are very concerned about it. So FeBr3, technically what we're looking at, if an entire molecule of bromine comes on, Lewis acid, bromine Lewis base, remember Lewis base has the lone pair, Lewis acid does not have the lone pair. If we do this, really what we're looking at got now the two bromines, lone pairs everywhere. What actually is going to be happening here is we end up just kind of kicking off one of our bromines. It's just going to go away. That means that the bromine here in dark blue technically steals its electrons. Oh, we have a negative charge on the iron, by the way, still. And so, if it leaves, we now have iron with 4 bromines, negatively charged. Oh my gosh, lone pairs forever. And we technically have a full Br plus next to it, technically. I'm okay if you draw it either way. If you draw it kind of just showing the partially positive bromine, or you can draw the full positive one next to it, kind of like a salt. Either way is okay. This is technically the more correct way, right here, where we end up with a fully positive bromine on it. So let's go ahead and use this bromine. I'm actually going to just use this little bit here as our electrophile because I don't want to redraw all those lone pairs. So let's go ahead and do it. Here we go. Here's our benzene. So just like the first step of an alkene reaction, our benzene is going to go ahead and attack the electrophile. What we're going to end up with is we end up breaking that double bond, right? Because its electrons are going to go attack the bromine. So what's going to happen is we'll have our bromine now on it, and we have a carbocation now as a result, right? There was an H. Remember, both of these, this already had an H, right? We're not going to lose that yet. But we're going to see that we're going to end up with a carbocation on the other one. We're going to have 1 hydrogen and 2 bonds to carbon, so we're left with the carbocation there. This, of course, can resonate around, so it is resonance stabilized. So we do see 3 different resonance forms here. And then, of course, we can resonate the other one. So remember, this is still resonance stabilized, so it's not as terrible as it might seem. And so we do have 3 kind of resonance forms here. We call this, by the way, all this stuff is called the sigma complex. When you have that positive charge as a result of your kind of first step here. So it's stabilized by all the resonance, right? So this carbocation isn't as bad as we might seem. But we have broken our aromaticity of the compound, right? So we're going to need to kind of restore that because everything wants to be aromatic. So I'm going to just start with our original molecule. Remember, it does resonate, but what's going to happen is now we can have another one of these bromines. Maybe this one will get off of the iron. It's going to come in, grab that proton, and reform. I guess actually I need to do a different color for these arrows, don't I? Because I have resonance arrows there already. Let's use purple. Okay. So we're going to go ahead and grab our proton and reform our double bond. So we're doing an elimination, addition, elimination in the same kind of mechanism. And so as a result, this is the purple arrows, we end up now reforming our double bond. And where did I have those? Here, I guess. And we end up producing HBr. And so we end up having our reaction take place. So first step, our benzene attacks an electrophile. That produces a carbocation that will resonate around throughout the sigma complex, as we call it. And that stabilizes it. And we're going to see that, of course, we can also have done our nucleophilic, or our elimination from this carbocation. We could have eliminated from that side as well. We would end up with the same product. So you can eliminate from either side. Doesn't matter. We have two like resonance forms that work there. The one with the carbocation opposite to it doesn't really help very much. And in fact, we see that the left and right resonance forms are better because of induction anyway. So we're more likely to hang around in one of those two as it is. And then we'll go ahead and have our bromine abstract the proton, and we will have reformed our benzene. Now with the bromine on it, that kicked out the H. So this H was from the original benzene. This is from the Br2. Both of those are from the Br2, right? So, and then of course we have our original benzene. And notice we get out again. I didn't necessarily write it this way, but if, I hate drawing the whole catalyst. Okay, I'm going to copy it. Technically, the bromine isn't just by itself. Technically, it's part of this big old thing. And what's going to happen is we're just going to go ahead and have one of the bromines leave off the iron, and it's going to go ahead and attack the proton. So that's, again, technically more what's happening. I'm okay if you write Br minus in a mechanism. And I'm also okay if you write Br plus for the electrophile part. So I'm cool with that. So go ahead.
So what is that?
That's the electrophile. So if we saw here, we added 2 Brs to our molecule, technically. What happens is that one just decides to leave, and now that is our Br plus. I'm going to just color code them so we can see all of them at once. So when the bromine molecule, when both bromines stick onto the iron, we're going to end up losing one of them as Br plus. And that one just happens to leave off. The electrons go to the dark blue bromine. And because of that, because both electrons go to the dark blue bromine, we end up with a lone pair now on that dark blue bromine. And because the green bromine only has 6 electrons, it has the positive charge. And it just hangs around like an ionic compound would, like sodium chloride or whatever, because it's Br plus and we have this iron minus complex. That's why it's going to just hang around there. Does that answer that? Yes. Yeah. So yeah. So this arrow there is that process. So the electrons between the 2 bromines that were there in their bromine-bromine bond, those electrons completely go towards the blue one. Okay. Cool. All right, and then we end up with our product. We're going to see, thankfully, the mechanism for all of these electrophilic aromatic substitutions are going to be the same. So we're going to learn a whole bunch of different reactions but there's really only three mechanisms. We're going to have one for substitution. We're going to have one for electrophilic substitution. We'll have one for nucleophilic substitution, and another one for addition elimination. So this was electrophilic aromatic substitution. And we're going to spend most of our time talking about this. And I'm going to just draw our generic mechanism. And we're going to see the mechanism, the only thing that's going to change is our electrophile and maybe our base. But it all follows the same kind of pathway. So benzene, some electrophile here will get attacked, whatever it may be. We then now have our benzene with the carbocation. Still have our H there, of course. Technically, we have an enantiomer, but we're going to get rid of it anyway, so it doesn't really matter. We're going to resonate. We just have that option, so it's a good idea to include it, that the sigma complex is capable of resonating, which is why, again, that stabilizes enough for it to happen. And then we have progressively worse and worse hexagons. We'll now have our positive over here, our electrophile and hydrogen. So again, resonance stabilized. This is our sigma complex again. Doesn't matter what our electrophile is. And then the last step, we have some sort of base. Base will come in and eliminate. We end up now with our product. So, mechanism for electrophilic aromatic substitution is going to be the same. So we have some electrophile. Generally, that will be positive charge or very strongly partially positively charged. Going to go ahead and get attacked by the nucleophile, which is our benzene. That creates a carbocation, which can resonate around, do its fun things. At some point, a base comes in and will pluck off the hydrogen, restoring the aromaticity of the benzene, and we will have effectively substituted our product here. And we would have gotten also whatever HB base, whatever that was. So here, E plus is our electrophile, and B minus is our base. So whatever that happens to be. So we're going to see in the last case it was Br minus, or technically the tetrabromo iron 8, iron 3,8, if I remember my nomenclature for 102. And so we're going to see here that that's going to be kind of exactly what's going to happen here. We can do it with chlorine. We just did it with bromine. We can do it. And here we can use a different catalyst, but the mechanism is the same. So the aluminum and the iron are interchangeable. We can do it. Just drawing the product here. Mechanism is the same. Haha, we can chlorinate our benzene. So just like with bromination, we just need the Lewis acid catalyst, and we're going to get our substitution product. And it's going to work exactly the same way as the benzene did. I'm sorry, the bromine did. So we have the chlorine sticking onto our aluminum chloride. We end up having one kind of more positive than the other. Technically, you can split off, form a full positive chlorine. We can have our negative aluminum tetrachloride complex. And we'll end up getting our product. Oh, we also have HCl as our byproduct, by the way, because we'll have Cl plus as our electrophile. Okay, so exciting stuff. So, any questions on the mechanism of what's happening here? So, scrolling up. Benzene attacks electrophile. Carbocation resonates. Base comes in, abstracts the proton, and we're done. Where does the aluminum go? It's acting just like the iron did. It's a catalyst. So just like technically I didn't write it before. So notice here, once that bromine leaves, we are left with FeBr3 again. And so that's just a catalyst, yeah. And so it's going to act the same way. So we started with FeBr3, wherever we started with, or in this case, started with iron, but it's going to form FeBr3. Here, if we do the same thing with aluminum, we're going to still get our aluminum chloride out again. And so it's still a catalyst. But this is a reagent. Or I'll say it's a reactant. There's not really a difference. So the chlorine, we do need equimolar amounts, or maybe a slight excess or something. But the aluminum, we only need a catalytic amount because it's going to regenerate itself. Okay. Well, let's take a look at another one. Very important one here. We're going to see that if we put benzene with fuming sulfuric acid, I'll explain what fuming means in just a second. We end up sulfonating our benzene. This is called sulfonation. I guess the other would be called halogenation, maybe. I don't know. I would just say substitution, but this one's called, well, sulfonation. And let's go ahead and describe what fuming H2SO4. That means that we have both H2SO4 plus sulfur trioxide in there. So we have both dehydrated form of sulfur trioxide with water added, making sulfuric acid, and we have plain old SO3 in there as well, sulfur trioxide. And if we look at sulfur trioxide, remember when we talked about sulfur? We described how in evidence, we might draw a Lewis structure like this, right, where we have sulfur with the expanded octet. Remember that there is evidence that we might actually have it more like this. Where we have sulfur with a 2+ charge on it. And so I'm going to go ahead and use the bottom part as our electrophile, because look now, we have sulfur with a +2 charge. That's going to be amazing, is it not? So let's go ahead and take a look at the mechanism. It's much the same. You just have SO3 as our nucleophile. If you use the SO3 as kind of written here, I'm totally okay with that. If you use it as the top Lewis structure with the double bonds everywhere, I'm cool. You can use it like that. So, but I'm going to, for the mechanism, I'm going to go ahead and use this one. So, benzene goes ahead and attacks. Actually, I think I will use the other form of the sulfur trioxide because it'll just make it a little bit easier in terms of showing the product. So I'm going to go ahead and use it this way. Okay, so in goes our benzene, attacks the sulfur, picks up some electrons. Remember that sulfur probably is not going to go above 12, so we're going to need to push those electrons away. As a result, we end up putting, oops, hopefully not double bond here. I'm going to just, again, for now, keep our sulfur with more bonds than it really needs, but that's okay. Carbocation here, H. I'm going to not draw all the resonance if that's okay. It's all the same thing, the double bonds within that cyclohexadiene, or the uranium ion, will just keep on resonating. Is that okay if I skip that? Same as before with the sigma complex. We just stuck on a different electrophile. Okay, so if now, I guess we just need our base. In this case, the base is going to be this dude. You may have seen this base before. Remember, sulfuric acid, as it's most concentrated, is about 96% sulfuric acid, 4% water. So there is always water hanging around in the sulfuric acid. And we're going to go ahead and abstract the proton, and we will get our product. But since we don't want it to be negatively charged, look what we've just made. We've just made hydronium. Look what's going to happen. Aha! We already have our acid at the end, so we don't need to wash it or anything. We'll just get our product. And so as a result, our water here is kind of catalytic. And so we end up now sulfonating our product. And so this is often written, as I did earlier, SO3H. That's why I kind of chose to just keep it this way. Otherwise, we'd have to deal with positives and negatives and things. So, okay. So this is a SO3H group, a sulfonyl benzene. Hooray. Beginnings of our toluene sulfonic acid, perhaps. Tosyl chloride, or I guess that's tosic acid, but similar there. So we have water here as our base, which then gets regenerated to protonate the hydroxy, or the negatively charged oxygen on the sulfur. And we'll end up with SO3H as our substituted benzene. So that's, again, why I drew it SO3H up here. I typically don't draw out the whole thing, but you are welcome to, if you'd like to go ahead and do that. And so, there we go. That's another one. So sulfonation. Special thing about sulfonation, though, is, interestingly enough, if you put some dilute sulfuric acid with it, it actually will leave. It'll go back to plain old benzene. Plain benzene. And for us, this is going to be extraordinarily useful because it means we can put on the sulfonyl group and we can take it off later. if we decide to. And we're going to see when we start talking about putting multiple things onto a benzene, that sulfonyl group is going to be very synthetically useful for us as what's called a blocking group. We're going to see later on, if we've already got a substituted benzene, that whatever is on your benzene can direct new things to different positions. And so we're going to see here that sometimes we want to block off a position from reacting, and so this is one way to do it, to install a blocking group like the sulfonyl group. So, again, or remember the reaction we just did, if we put the fuming sulfuric acid, we can go back to the sulfonated form. So, very useful. All right. So again, the mechanism is much the same. Just throw in a different electrophile at a different base. Guess what? We're going to do it again with nitration. Any questions on that? Oh my God, my throat's so dry. Anyone have any questions on this one? Yeah, so you can just cycle this through as much as you want. So put your concentrated fuming sulfuric acid on benzene, it turns into the sulfonated form. Throw dilute sulfuric acid at it, it goes back to benzene. So you can, it's essentially reversible, but we use different reagents to do it. All right, next one. If we put nitric acid with sulfuric acid, we will end up nitrating our benzene. Very exciting stuff. Guess what? The mechanism is exactly the same, but as before, I want to show you how we generate our electrophile. The last one we saw, SO3, it's kind of already its own electrophile, so we don't really have to generate it. But with the nitric one, the nitric acid, we do need to kind of show how this is generated. So, remember we have positive nitrogen, we have, I guess one of these should have an H on it, right? Then we have a negative oxygen. We're going to see that what we can do, sulfuric acid is much stronger of an acid, right, than nitric acid is. And so what can happen here is we can have a proton. The sulfuric acid will kind of react as an acid with nitric acid as your base. Isn't that mind-blowing? Nitric acid as a base. And so we end up getting I specifically chose not to use the negative oxygen here for the following reason. Is what happens is we're going to end up actually kicking that off as a leaving group, essentially. OH2 positive, water, is a good leaving group. And so we end up with this thing. The nitronium ion, which has a positive charge, thereby making it a good electrophile. Right? Positively charged things are great electrophiles. And so we're going to see that in order for this to react, we need a strong electrophile, right? And here we go. Here we go. Attack our electrophile. Notice nitrogen can't have more than 4 bonds, right? So we're going to go ahead and pop one of these carbonyls, not carbonyls, nitroso groups open. We end up nitrating it now. And that's still a positive nitrogen, by the way. Okay, and then again, resonance that I'm not going to draw. It's just moving that carbocation around. And look who is here, but our best friend OH2, who I'm missing a lone pair on. The water that we made right here, that is now going to be our base. And ta-da! Mechanism you should have probably memorized by now because we've done it 15 times. And so we now have our nitro group on there. And yeah, we're going to lose our H3O plus by doing this. But that's okay. Again, the sulfuric acid, it's kind of already there. So, okay. So there's nitration. Any questions on that one? Same old thing. So we generate our electrophile, the nitronium ion, by protonating nitric acid, and then the nitric acid kicks out the water. It dehydrates. Sulfuric acid is a potent dehydrating agent. So we lose our water. We end up with this positive, well, this cation here. And we're going to go ahead and react it as an electrophile. And then go through our standard elimination procedure. And there we have it. End up nitrating our benzene. This one can actually do other things, though. Once we have it nitrated, if we treat it with a transition metal and some acid, and then apply a base, well, technically, we'll do it in 2 steps. I'll show you both steps. If you treat it with a reducing agent, you can end up kicking out the oxygens, you end up installing some hydrogens on there. Giving it a base will then transform it from nitrobenzene into aniline. So we can, I wrote it out in 2 steps here, just to show you what happens in each one. So we end up, you don't need a mechanism for this. You end up replacing your oxygens with hydrogens, and then you take one of those hydrogens away to make it not cationic anymore, and you end up with aniline. So as long as you write it in 2 steps like this, you are just fine. So this is step 1. That's a positive number 1. And then this is step 2 here. So we can now take a nitro group and turn it into an amino group. We're going to see that this is extraordinarily useful. So, questions on nitration or the subsequent reduction to the amino group? For this reduction, again, you do not need a mechanism, you just need the reagents. You can use either one, iron or zinc. It's fine, either one, take your pick. Both of those will work here. Okay, so those are just reducing agents. Yep. Of course. Is this good? Cool. Okay, let me know. And so, yeah. Nitration. Yeah. Let me write it. Yeah. Nitration. And this is just, I mean, this is generic reduction, yeah. So I'm going to scroll down just a touch. So the process of putting the nitro group on is called nitration. And then you can reduce your nitro group to an amino group. Okay. Cool. Okay, so this is just reduction. On one of the next ones, we will actually have a fun name for one of them. So, hooray. All right, let's keep on going, though. So we've now added, let's see, we've been added to add halogens. We've added sulfonyl group. We've added a nitro group, which we saw that we could adapt to adding an amino group by reducing it. Great. Let's keep going. We have more. Guess what we can do next? How about we can alkylate something? This one actually has a name also. Friedel Crafts Alkylation. So we have a name. This is something that I think you guys do as a lab, but I don't remember. So how this works? Notice our dear friend aluminum chloride is back. We will put an alkyl halide in the presence of a Lewis acid, and we're going to end up alkylating our benzene, sticking an alkyl group onto it. So let's take a look. What happens here? Again, most of this mechanism is just the formation of the electrophile, and so that's the big part. The rest of it's exactly the same. Once you form your electrophile, it gets attacked by benzene. Benzene resonates. Base comes in, plucks off your hydrogen, and you end up getting your product. So here we go. Let's take a look here. Lewis acid, remember, means that it is going to accept a lone pair. So here we go. Lone pair comes in. I mean, I kind of want to just write this in one step, but I'll be good. We now have, just like before, I'm not going to draw the lone pairs on the rest of the chlorines, who cares? And then what happens is, just like with the what was it, the bromine, we are going to kick out, or those electrons are going to go ahead and go onto the chlorine, leaving us with, I kind of want to write this to the side or something, but hey, I'll do it, yeah. Okay, we end up with this thing. We have now a carbocation alkane. That's our electrophile. And notice, because it is a plain old carbocation, if we had positions to rearrange this carbocation onto, it would do that. So here we have it on the secondary position. That's the best position in this particular molecule, so it's not going to rearrange. But if we did have a tertiary spot nearby, it would go there. remember that carbocations will destroy molecules, right? They'll do whatever they can to stabilize themselves. So we're going to end up potentially messing with things if we have a carbocation that can rearrange. So as a result, by the way, if you tried this, or here, let's just go ahead and do this reaction, and then we'll take a look at a few instances where you can't do this sort of reaction. Okay, so we have our electrophile, benzene, and our carbocation here, benzene, gets attacked. I'm going to just draw it sideways, if that's okay. I'm going to skip all the resonance because, again, I showed that the first like 3 times, and we don't really need that anymore. Here comes now our dear friend, the aluminum complex from before. It's technically negative here. And poof, we end up with our product. And we lose HCl. So again, our AlCl3 is catalytic, so it gets regenerated. We end up with, I'm going to just put it on this carbon instead, same thing. So we will have attached an alkyl group onto our benzene. All right, so how the electrophile forms. Our chloride ion, with its lone pair, acts as a Lewis base, attacks the Lewis acid. I'll write those out, because why not? Remember, Lewis acids accept electron pairs. Lewis bases donate electron pairs. We end up with a positive chlorine, negative aluminum. The positive chlorine ends up taking the electrons that currently bind it to the alkane, or what I guess at the time is an alkyl halide, thereby releasing the carbocation alkane, which then potentially could undergo rearrangements, as carbocations are so very wont to do. And now we have our electrophile. That electrophile gets attached by benzene. Then the aluminum tetrachloride ion comes in and plucks off the hydrogen, producing HCl. Sorry, I didn't scroll down for that, but it's there. So, if we take a moment to look at some electrophiles, we can do that. And so we'll take a look at that in a second. Give you a second to copy it here. Okay, just going to scroll down a little bit. Just to show you some of the electrophiles we could make. Ethyl and methyl are kind of our only ones that we can make primary with this process. Because in these, there's nowhere for that carbocation to rearrange. So if you want your benzene to be attacking a primary carbocation, you can only do it with ethane or methane. So 1 or 2 carbons, that's it. The minute you throw propane in there, you're going to end up rearranging your carbocation. If you were to try it, let's take propyl chloride. Oops. you technically get your carbocation here, but look, you're going to end up having a hydride shift, and you're going to end up rearranging your to the middle one, to having the carbocation secondary. So again, carbocations will rearrange if they can. They will find a more stable position, and they will do whatever is necessary to get there. So you're going to see then, as a result, that even if you put plain old propyl chloride, you are going to end up with the isopropyl benzene. Doesn't matter that your ideal electrophile was the N-propyl, the linear propyl, you're going to end up with isopropyl because of the carbocation rearrangement. So just be aware of what can happen there. So remember, carbocations can move a hydride, they can move an H, they can move a methyl group. In rarer circumstances, they can do other things. They can do ring expansions and all sorts of crazy stuff. But primarily you're looking at hydrides and methide shifts. So just be aware of those. This is also kind of a crappy reaction to begin with, because unfortunately, we're going to see in a little bit butyl chloride. Or you could use, that chlorine could be on any of the carbons. It'll rearrange itself, but might as well just have tert-butyl chloride anyway. What we're going to see is, oftentimes, we will end up polyalkylating you'll end up putting multiple of these groups on. The reason for that we will kind of explore. I think we won't have time today, but we might. We're going to see that alkyl groups, because they donate electron density, remember alkyl groups are slightly electron donating through hyperconjugation. Because of that effect, you're adding more electron density to the benzene. That makes it more nucleophilic, right? The more electrons you have in your nucleophile, the better. So, as a result, that makes the benzene more reactive towards this alkylation. And so it's going to say, oh, why did I just grab one tert-butyl group? I can have more. And so you'll also end up polyalkylating your product here. So sometimes this is not the best reaction to do. So just beware of that. So sometimes you don't stop at just putting one on. Chances are in the previous one with the propyl chloride, you're going to end up with isopropyl on the other side too. So, same thing, polyalkylated it. And so you'll have extra alkyl groups, more than you wanted. So, we're going to learn a way to get around that, though, especially if you want to put a primary position onto our benzene. So, by the way, one way to prevent polyalkylation would be a sulfonyl group, right? If you put an SO3H on one of these positions, well, you're going to see that it's not really going to work anyway, because we'll get into there. But that would be one way to prevent this from happening, if you block off the position with something else. Alrighty. Any questions on that one, by the way? So we have a problem here. Okay, couple of things to point out. So polyalkylation is a problem. Another thing is, if you have a nitro group and you try this, if you try this, Not going to work. And this is something we'll focus on more next time, but if you have an electron withdrawing group on your ring, it's going to make it so less reactive that it's not going to be able to take place. So we're going to see that the nitro group being so electron withdrawing will prevent this reaction from taking place, the Friedel-Crafts alkylation. So even though normally it works with plain old benzene, works better with some sort of alkyl benzene, it will not work at all with nitrobenzene. So we're going to see that substituents have effects upon it. We're going to have a whole list of things that make it more reactive and things that make it less reactive towards electrophilic aromatic substitution. That'll be fun. Another thing, this also doesn't work with vinyl benzenes or whatever. Aromatics. So you can only use sp3 alkyl halides. So all these sp2 or sp1s will not work either. So remember that carbocations need to be stabilized, right? We saw that the opposite is true for anions, right? Anions like being on sp or sp2 carbons better than sp3. Carbocations are the other way around. They want more hyperconjugation to stabilize them. So we see that sp2 or sp carbocations don't generally exist. The anions, yes. The cations, no. So if you're going to put an alkyl group onto your benzene, it has to be from an sp3 hybridized alkyl halide. So none of these sp2 or sp business chlorides can happen. Okay? Leave this screen up for a second there. We have one more reaction to learn today. Fun. But look at how many you've done so far. I really like this chapter because there's so many things we can do, and it really allows you the opportunity to very analytically focus upon doing a synthesis. And because we're going to see that putting things onto benzene, sometimes the order that you're putting them on affects things. Sometimes, you can end up guiding things to different positions. We'll see. It's cool stuff. Alrighty. Cool. The last one, our last electrophilic aromatic substitution reaction, is again a Friedel-Crafts. But this time it's an acylation. Acyl is different from alkyl. Acyl means there's a carbonyl there. So, just like before, take our benzene, we put an acid chloride, and guess what? Ta-da! We will acylate our compound. So we're going to stick on a carbonyl with whatever else happened to be there. And guess what? First, we're going to look at how the electrophile is formed, and then we're going to go ahead and see the mechanism. So, guess what? Look here. This should be a new and surprising reaction. Uh-huh. Who knew Lewis base chloride goes and attacks Lewis acid aluminum chloride? And I mean, thankfully, this is so repetitive that it makes it easy to learn because it's the same thing that's happening every single time. Who? Anyone care to guess what's going to happen? Oh my heavens, you got it right. Thereby leaving us with this with our carbenium ion, or positive, whatever this carbocation. There we go. This carbocation is especially good because it is resonance stabilized. This does have resonance. This is better than the alkylation. So the alkylation, we had incomplete octets because we had carbocations, right? Here, we're able to resonate such that we end up having full octets on everything. And this makes it particularly good as an electrophile because it's not so reactive that it's going to like explode or anything or destroy itself to try and get to a better position, but it's going to be a little bit more stabilized. So this is a good thing. And as a result, we don't actually see rearrangements either. So we don't see any, with this carbocation, we don't see any hydride shifts, methide shifts, whatever, because we're able to do this oxygen resonance. So, write that up. This resonance means no carbocation, no rearrangements are necessary. Hooray! So with the alkylation, we saw that if there's a position to move your carbocation to stabilize it, we would. But here, that oxygen is going to be able to stabilize our carbocation far better by getting rid of the incomplete octet. So we won't have that problem anymore. Okay, so we'll leave that there for a second. And then I'll go ahead and do the same thing as we've done before. Let's do it. Benzene. I'm going to leave it as that stabilized form, because that resonance contributor is probably the most stable. And up now with our, oops, I forgot our carbocation. And what a surprise, look who's here for the 50th appearance today. Oops. Fix it out. And we get our product. So, ta-da! We again regenerate our AlCl3. So we have saved our compound. Hooray. All right. Business as usual, same mechanism. Let's take a look at what we can do now. We have one last little bit here. Here, let's do an example of it. So if we want, we can acylate this. Our group stays the same. Thankfully, we know a couple of ways. Have you guys learned the Wolff-Kishner reduction? Probably not. No, that's probably something we'll talk about in the next chapter, actually. What we can do with this is we can actually get rid of it by doing a reduction. This is called a Clemency reduction, by the way. And of course I have no space, but what it does is it just gets rid of your carbonyl. Boop, 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 boop. So we just get rid of that C double bond O. We're left with the alkane. Alkyl benzene, rather. This time it's not an optional reagent. That is zinc and mercury alloyed together. It's called Zinc Amalgam. But the last time we saw this, we had iron or zinc. In this case, it's both zinc and mercury at the same time. So that means that it's an alloy and mercury. Put in that with some hydrochloric acid, add a little bit of heat, you will reduce your carbonyl away and be left with the alkane. Again, alkyl benzene. So this is a better way to put the alkane on, because one thing to note is a carbonyl will deactivate your ring. It's electron withdrawing, right? So we don't have the opportunity for polyacylation. Alkyl groups activated our rings, so we did see we could get polyalkylation if we use alkyl halides as our electrophiles. However, if we use the acyl halides, we end up deactivating our rings, so we don't have polyacylations happening. And so if we only want to put one alkyl group on, best way to do it is put it on as an acyl group first, and then reduce it down to the alkane. And that means you can also put a primary, what would have been a primary carbocation. So, very useful thing here. So let's take, let me write all that down. So because is an electron withdrawing group, the benzene, or the ring, gets deactivated. And so as a result, polyacylation is not possible. So that's a good thing. We typically don't want to have a mixture of products, some with 1, some with 2, some with 4, who knows what. You can get all sorts of weird things happening with alkylations, but acylation, you can avoid that problem. But then it is 2 steps, so just be aware of that. So first step, you'll put your acyl group on. Second step, you will reduce it. No mechanism for the reduction, just like before. However, for the phenol Krebs acylation, yes, you would be expected to do that because it's really the same mechanism as all the other ones, right? We have benzene attack electrophile, base comes in, takes proton away, and poof, we're done. Substitution, elimination. or rather addition elimination. Cool. So scrolling down here again, because we have that carbonyl there, it ends up pulling electron density out of the ring, thereby making it less reactive towards electrophilic aromatic substitution. Alrighty. Questions on that one? Alrighty. That's all of our electrophilic aromatic reactions. So we've done halogenation, we've done sulfonation, and desulfonation, I suppose. We've done nitration, and then we also saw we could reduce that nitro group to an amino group. We've done alkylation, Friedel-Crafts. We've done acylation, Friedel-Crafts. We've also seen the Clemency Reduction, which gets rid of a carbonyl. And I think that's all of the ones we've done. So, hooray. Lots of reactions here. Tons of reactions in this chapter. But what if we don't have plain old benzene? But what if we're not using benzene as our starting material? What if we use something else? Say, toluene. Our dear friend toluene. Click an H. We're going to see that if we have toluene, it's going to be, for this reaction, about 100 times more reactive. Isn't that interesting? Already just 100 times more reactive because you have an alkyl group on it. So donating a little bit of electron density. We're going to see that because of that, it'll be easier when we talk about stronger groups. We'll see the resonance here. But we're going to see that we end up with 3 potential products here. Go ahead and just draw a parallel over here. So we end up with 3 potential products, right? We don't know yet which position is going to be nitrated. And we're going to see that it's roughly, I have the numbers written down here on my notes, 63%, 34%, and 3%. So, why? Why do we get these? Well, first things first, we see ortho is the predominant product. The reason for that is even though para is better for steric reasons, methyls are pretty small substituent, right? But still there's some steric bits there. So para is technically the preferred position for this. But notice we have 2 ortho positions. And so each of those can get, or it can attack the nitro group. And so as a result, we're going to end up with twice as many options for the ortho as para. And so even though para is a little bit better, we can consider each ortho to be half of 63, which is what, 31.5? But since we have two ortho positions, that ends up winning out in this case. So let's take a look at the mechanism real quick, and we'll see why this is going to be the case, that we're going to end up getting either the ortho or para preferred over the meta position. So here we go. Okay, so we have our here we go. Tax opens up. In this case, the resonance is going to become more important, so I'm going to draw it in a separate line, and I am going to draw all the resonance. Okay, so we can resonate this thing around. H there. I'm sorry, that's not in H. We have oops. Sorry, if we put our nitro group there, we end up with our positive charge here. Right? And so, it's a relatively stable position, yes. We see that because that is now a tertiary allylic carbocation. So that's a good place. It's a good place to add our nitro group because we end up with a tertiary carbocation. If we try and resonate that, or if we resonate that, lucky us, we can end up with our carbocation in various places, but the best place is right here. So this is a good place to add our nitro group. If we want to add it to the para position, if we do that, if we attack our nitro from the para position, we're going to look at all the carbocations we get here. So here we go. We're totally going to be out of time, but I'll just zoom through it real quick. We're going to see that we end up with the carbocation here, and guess what? That one can resonate onto the tertiary position. So this one can resonate there. And I guess we're out of time. But we're going to see with the meta one that we don't end up getting that. We end up getting our carbocation adjacent to the tertiary positions. It's still secondary. So we're going to see that's the reason that we don't typically see the meta position being taken up here. So suffice it to say for now, we're going to just leave this off. We're going to pick it up next time. So we're going to keep on going. So I would definitely start learning these because next week we'll start synthesis with it. So we're going to learn the rest of the reactions, and then we're going to spend a bit of time trying to figure out how to make polysubstituted benzenes. And this is probably something you'll do in lab as well, but it's a very important skill for us. So be prepared to participate on Monday too. So it'll be fun. Alrighty. I'll see y'all later. Enjoy your, oh come on now so you can do it. Enjoy your whatever weekends. See you next time.